back for Dynamics ES211. Here's homework 14. Homework 14 is very similar to homework 13, or at least the first two problems are, because we are doing the same problem, but this time we're using instantaneous center of rotation. Sometimes it's easier, sometimes it's more difficult. We'll see because of the geometry. But so this problem right here, we have this just a bar, and we know one of the velocities, VB, it's going up, and we know that A is constrained to be in the x direction, move only in the x direction. We want to find the velocity of C, but we want to use the ICR method here. So here we go. Here is the problem written out. And so our first task quite often here will be, let's see, I didn't write VC here, no VB, that's the velocity of B, and since I gave an arrow, that would be appropriate. It's going 5 inches per second upwards. I kind of made it look more like that was 30 degrees. How close is that to being, it's supposed to be 25 degrees, yeah. No, it's actually more than 30 degrees, right? So there's 30 degrees right there. So be careful to make a careful sketch of these. Let's see. So first off, I'll just draw this thing out. There you go. And I will put a velocity upwards here. Now, the velocity here is going to go horizontal. So what we want to do is we want to draw lines perpendicular to their line of action, right? So the line of action is right here. So this one will have a line of action that goes like that way horizontally. This one is going to have a line of action that goes vertically right there. So right here is the ICR. And that makes it if it was only this would be a really easy problem right here. So this is the ICR right here. And so looking at this, it's obvious that it must be rotating this way here. So we could say that omega ABC is equal, it is rotating right around there. If that's the case, that must mean that the velocity of A, I said velocity of C, that should be velocity of B, whoops. Velocity of A is going to go in that direction right there. Now the position right here, I'm going to call this R, and this is going to be B with respect to ICR. I made that very small. And this right here is going to be the R of A with respect to ICR. Easy enough. So we know that the velocity of B is going to be equal to omega ABC times R B with respect to ICR. And we can find that R B with respect to ICR easily enough because we know this length of AB is 4 inches. We know that the distance right here, since this is 25 degrees right here, that we're going to take, it's going to be 4 times the cosine of 25 degrees. And therefore, let's see, 25 degrees, cosine, and then 4 times. So we get 3.625, and that's going to be inches. So if we want to find omega, we want to find what this is right here, just solve for this. Omega ABC is equal to VB over RB with respect to ICR. Or you're going to find that it's going to be 5 inches divided by 3.625. So omega ABC is going to be 1.379 radians per second and it's going to be going clockwise. If you were to look back at what we found in problem 1 of the previous homework right here, you could see that this 1.379, and we had a negative. We used vectors to find it. So you can see there's a lot more stuff that we wrote all the way there to get to that spot compared to what we did right here. So in this case, ICR, much easier method than using vectors. But here's the thing. Now we didn't get asked what the velocity of A was, but we could find it really quickly because we could find RA with respect to ICR. It's just going to be 4 times the sine of 25, right? So the sine of 25, we're going to get 1.690 inches. So now all we need to do to find the velocity of A is just take omega ABC and multiply it by RA with respect to the ICR, or 1.379 times our 1.690, and we get 2.332 inches per second, which is what we found before, right there, right? But I don't think we were asked that as part of the problem, but hey, it's good to know. All right, so let me just pause for a second because I got an email, so sometimes that's a student. It was not a student. Okay, so here's a difficult one though. Now we're going to have to mess with the geometry. Now in order to find the velocity at C right here, we need to find this ICR. Now this is gonna, I wrote all over this, so this would be kind of hard to see, but that right there is the thing that I want to find. Let me redraw this. If I had planned the thing out a little better, it wouldn't be as much of a hassle to write the thing out. But here was the velocity. Here's that point, here's this point, and here's this point at C, right? So we have that our ICR is right here, ICR. But if we want to get the velocity at C, we have to get that length right there. That's a little bit of a geometry ask. That's hard, but we can do it. We just have to be a little systematic about it. And I think drawing some side diagrams, and I don't even remember exactly how I did this, but one of the other things we're going to need, we're also going to need this angle. So we're going to need this length, and we're going to need this angle. And we could do it in a couple of different ways. I don't, I tend to want to break them up into smaller triangles, but looking with what I have available right now, I think I need to break it up into smaller triangles. I don't think there's any way to make this easy. So the way that I would go about doing it right here is to extend this line right here and extend this line right down there, okay? And I know this distance right here. I'm going to be able to find this distance, and I'm going to be able to find this distance. So I have this bigger triangle right there that I can find, because I really want this distance right there. I didn't do a good job of that, but that's going to be RC with respect to ICR, and I also want this angle right in there, which I would maybe want to call something besides theta, because we were using theta up above. I'll call it beta. That angle right in there I want to find, because then once I know that, I'll be able to think through and figure out. By the way, we know that our omega ABC is that direction, so our velocity C is going to be perpendicular to this. Did I do that right? Let me see. I did not do that right. My bad. I used this line, I should use that line. So here I'm going to make this perpendicular to that line. It's not going to look that much different probably, but it's important, right? Right? And when I do that, when I'm done with that, by the way, I'm going to see that that angle is going to be the same thing as this angle right there, right? And then I'll be able to tell you, once I can subtract 90, this from 90, and that will be the answer. So I want to get my RC ICR from this little diagram. What I'm going to find is going to be the square root of this length right here, which we already have actually. That is the same thing as this length. So that's going to be our 3.625. Whoops. But now I need to add to it before I square it. I need to add to it this length right here, which is going to be, it's going to be, I didn't make it long enough here, so I'm going to do this in parts over here. This is going to be 6 times the, because this right here is theta, 6 times the cosine of 25, which is going to be equal to 5.438 inches. And then this, okay, so that's going to be 5.438. All right, and it's going to be that quantity squared plus, and now I got to get this length right in there. And so that's going to be our 6 times the sine of 25, which is going to equal to 2.536 inches. So it's 2.536 squared. And let's see, I take 3.625 and I'm going to add that. So that ends up being 9 point, maybe I'll even write this out right here. Move that down a little bit. Write this out as an in-between number, 9.063. And I'm going to square that. And then I'm going to square this guy. I'm going to add them, take the square root, and I'm going to get the RCI. C with respect to ICR is 9.411 inches. And while I'm here, I'm going to get this beta. And beta is going to be the inverse tangent of this rise, 2.536, over this run, which is this guy right here, 9.063. And so 9.063, whoops, I did the wrong way, but that's okay, I'll flip it. 2.536, and we're going to take the inverse tangent of that, and I get that it's 15.63 degrees. Okay, so now I'm ready. I'm armed and dangerous. All I need to do to get my velocity of C is take omega ABC, which I found up above, and multiply it by R, C with respect to ICR. And what we end up getting is 1.379 times R 9.411. And 1.379 times that, and I get that it's going to be 12.98 inches per second, and the angle that it's going to be here is going to be this right here. Here's beta right there inside that angle, so it's going to be coming upwards at 90 minus this right here. So 90 minus 15.63 is 74.37 degrees. So our answer to this problem, VC is equal to, let's call it 13 inches per second, and is coming upwards in that quadrant at 74.4 degrees. All right, so let's box it. Why didn't that work? What's it going on? And take a look. This is not a good scan. This is a terrible scan. I got to rescan this. I accidentally, but you can see that's what I got. 13 inches per second, 74.4. Mostly easier than doing it with vector math, but getting this line and getting that angle took a little bit of geometry finesse. It could be a little frustrating, but I've done problems like this before, so I have seen it. But as you're trying to do it, you might find that the ICR is easy when it came to doing this part of it right up here, right? Very straightforward, but then like you try to get up to there, and it's like a geometry test, right? And who wants that?